Okay, so the first thing I'm going to do is create a folder with the name of the compound, which is 6E8G, sorry, 1GX4X. That's the stapled version, so that's S in front of it. I'm leaving out backslashes because that's going to mess with the computer finding the right files. All right, and then within that folder, I'm going to copy over something that I already have made, and that's oh shoot, let's see if I can find it. It's the a PDB file for the coil variant that is just all natural. And this has already been through all of the prep that you got to do to a PDB file to get it ready for Amber. So
is that the prep that we've done in the past?
Okay. Missing heavy atoms have been added if there were any. Crystallographic waters have been removed, and hydrogens have been added. So if we didn't do anything, this would be ready to go. I just put it there in the folder, and this is dumb, like you don't have to do this, but I kind of like to have a paper trail for what I've done. So I keep, even though I've copied that in the folder from someplace else, I duplicate it before I do anything to it. And I rename this one the name of the compound dot build. And I'm going to use that and edit that to build what I want to do. So for you, you're going to be copying this up to the supercomputer. There's another file you're would need for this. I have a separate folder on my computer in another location where I have files from Staples. And so if you were going to do this, I would have to copy this and make this file available to you. But if I double click on this particular file, the name tells me it's a propargyl glycine that has a PEG staple in between two propargyl glycines. So there it is. It's one of the optimized structures. I used several of these to derive the charges. But basically, we don't need everything. Over here, you've got the nitrogen, alpha carbon, carbonyl carbon, and acetyl group, and methyl amide. And you got the same thing over here. Now, all we're going to need to build this staple is all of the backbone atoms are going to be in place already. All we're going to need is the beta carbon and beyond. Each of the atoms in this staple is going to have a name and a residue. So the way I've divided it up, let's see if this is, no, that's not what I wanted. The way I've divided it up, all of those atoms in yellow are the propargyl glycine residue. I have a different three-letter code for propargyl glycine on its own. For propargyl glycine in this kind of staple with the triazole, I gave it the three-letter code PRB. No reason other than that's what I chose. All of that's in the supporting information of my paper. I've got some figures that you can look at and refer to in the future. Within each of these atoms, well, within this residue, each atom has a name. So the alpha carbon is C alpha, the beta carbon is CB for C beta, the gamma carbon is CG, delta carbon is CD for C delta, and then the hydrogens are named according to what atoms they're on, and I'll show you some of that later. So the staple is going to have two of the same kind of residue on either side. Then we're going to name the atoms of the staple as its own sort of separate residue. It doesn't totally matter that you do this, but I decided to sort of break it out conceptually. So there's a PRB residue on this side, a PRB residue on this side, and then a separate residue for the staple in the middle. And that's going to comprise the three atoms from the triazole ring, the three nitrogens. and then each of the atoms in the chain. They're going to be named basically according to Greek letters, um, and I'll tell you more about that later. But we're basically going to paste this structure into the PDB file. Once you get the PDB file uploaded in a place on the supercomputer and you get Gaussian going, you can come here to open and then navigate to that PDB file and open it. On a desktop with a Mac, I just right-click Open in Gauss View. And that will then open my protein. Just to get oriented, there's some things that Gauss View is able to know and interpret from the PDB file, and there are other things it isn't. For example, right here is a disulfide. It doesn't know that there's a bond there. And it's so you can actually come up here. There's a button that has an arrow between two spheres that are connected by a line, and you can say, okay, I want to that's how you adjust bond types and distances between atoms. So you can go there, you can click on this two sulfurs, and you click this with OK, and that will put a bond there. And hopefully that'll, if we press save and save this as a PDB, that'll write that as a connection. Sometimes Gauss View gets it wrong. You can actually go into the PDB file manually and tell it what's connected, and I'll show you how to do that. What we want to do now is find the two side chains we need to modify that are going to be stapled together. We're going to have to delete the side chains that are there, and then we'll paste in the staple and makes the right connections. Your friend, when doing this isn't like PyMol. There's no sequence up at the top, so it's hard to get oriented. So what's really helpful is Tools and Atom List, and this opens up a window. There are a lot of things you can display about the atoms, some of which are relevant to you and others are not. I've got coordinates, though you don't totally need them. That's C. And then P is for PDB, which this will tell you the residue name and number, and it will tell you the atom name. That's really, really useful. So what I do is I just, I actually, it doesn't remember this, but I readjust the window so that I can look at the structure at the same time as I'm looking at the atom list. Right, so then there's a couple of things about this PDB. They're not divided up into chains. It just numbers residues from 1 to like 70 something or other. Oh, I need to expand that just a little bit so we can see the numbers. Yeah, so the last residue is the N-terminal, C-terminal amide residue 74. The first residue is the N-terminal acetyl group, residue 1. That's different from how we number our sequences. If you look at your SI, which shows the names of the structures, you can see we start counting on 1. So you sort of have to adjust your counting and make sure you get the right residues here. In our nomenclature, 6E, 1, whatever, G, the first number refers to the acidic subunit A, which is the one that begins with glutamate, and that's the same order that's in this PDB file. The sequence begins with glutamate. So we want to modify the 6th amino acid here, and then we'll need to come and modify the first amino acid in subunit B. Does that sort of make sense? Yeah. All right, so navigating around, one of the things that's really helpful, so we'll go to, let's see, residue 6. In the unmodified sequences in E position glutamate, that would be glutamate 7 here, and there it is. I can come here and I can click on atoms within that residue. If it only lets me click one at a time, you just come up here to the menu, click View, and you uncheck exclusive highlighting. If exclusive highlighting were checked, it would only let me check one at a time. It's helpful, though, to label more than that. So I'm going to highlight all the backbone atoms, the N, and you can see their atom names here, the NH, the C alpha, the HA, the C beta. Now we're going to get rid of C beta because we're going to import C beta from the staple. So we just want NH, C alpha, H alpha, and then down here the carbonyl carbon and the oxygen. Now here's the really useful part. You can see that I've highlighted them, but and I could zoom in, but if I go View, Center Highlighted Atoms in View, and then zoom, on my mouse to zoom in Gaussian is a right click with motion up or down. That may change depending on whether you're using a 2-button mouse or a 3-button mouse. On my Gauss view, if I press the Shift button and click on any atom with left click, I can move from side to side. And I'll show you some of that a little bit later. So there is you can see the glutamate residue we want to modify. And all we're going to do at this point is delete the unhighlighted atoms. So to
That's
do
the whole thing. Just kidding.
Yeah, yes, everything except that. No, sorry, of that side chain.
Yeah.
Thank you for that clarification. So you'll come up here to the menu, and it will look something like this: a red X, and a line, and a sphere. You click on that. That's the delete tool. Fortunately, in Gauss View, anything you do is undoable. So if you screw up, you could just Control Z, which isn't true in PyMol.
It is undoable.
Right.
I thought you said it isn't.
No. Sorry.
That was high stakes.
No.
Yeah, that is really annoying about PyMol.
So I'm just going to click the atoms in the side chain one by one. We could also, in principle, go manually through and just delete those lines from the PDB. All right, so what we've got there is what's left.
Did you do that before you put it into Gaussian?
Yeah. Though if you do that, Gaussian's going to tell you it's not sure what to do with that residue because it doesn't have all the right atoms.
Yeah.
Okay, so we're done with that for the moment. Now we'll come back over here, and I'm just going to uncheck these. And then we need to scroll down, and we got to go until we see these three NH3. That's the C-terminal amide of the A subunit. Then we're starting again with 38, which is really 1.
Yeah.
So we want to install the staple for this variant, which is 6E1G.
So
It'll be the first
lysine.
residue, that lysine. So again, and I just do this to keep, I made so many mistakes that I try to just try to do it the same way every time, keep myself organized. So I don't. Just a minute, I'm recording something right now, so I've highlighted NHC alpha, H alpha, and then the carbonyl carbon and oxygen. We'll go back to View, Center Highlighted Atoms in View, zoom in, rotate around to get a feel for where the side chain is. Sometimes it takes a minute to see it. The other interesting thing that I didn't mention before is each atom in a PDB has a number. And that number will be displayed on the atoms over here. So if you ever get confused about where you are, you can come back here and view it. Okay, so I'm just going to delete everything in that side chain that's not highlighted. I'm going to try to get a clean shot so I don't accidentally delete things that I shouldn't. And we're still on the red X, so oops. Sometimes if you delete carbons, it will delete everything that's attached to the carbon, which is nice, but also scary.
Yeah.
Okay, that's it for that one. So we now have two different side chains, 6 and 1, that are truncated. And just to view them again, I'll highlight them. So, and you can see good, they're close together. That's good for us. All All right, so now is the fun part. We're going to staple, we're going to paste in the staple. Staple in the staple. To do that, I'm going to come up to the menu bar, and there should be a tool that has an arrow with a little dotted line square. That's a select by highlighting, or select by, I don't know, whatever that's called, where you click and drag. That selects all the atoms. You can either do Control C, or you can press this copy button up in the menu line. That copies this structure, so you don't have to build it from scratch. That'll help because the atoms in this structure are listed in an order that makes sense. They don't have to be, but I made it that way. They're listed in an order that makes sense. They're not named or anything, but they're listed in an order that makes sense. That'll make it easier to name them later on when we're modifying the file. So now we'll navigate to the other window, and all we're going to do is come up here to the paste button, which is the clipboard and the little blue thing, and you want to choose not add to molecule group, but append molecule. That pastes the molecule into this file. Now you can sort of see what happened there. The molecule's like clear over here, and that's kind of weird. And so we got to get it into position. And to do this, you press on my keyboard. I don't know how it is with on the supercomputer. You press the Option key and the Shift key, and that allows you to click on the one molecule without moving the other. So that's how you move them relative to each other. And you sort of have to move this around in look at it from a few different angles to make sure you're getting it sort of near. Your goal here is not to have it be like perfect, but to have it be somewhat close. And if you want to rotate the staple, just hold down the Option key or the Alt key while clicking on the structure, and then you can move it around, rotating it in space in a few different dimensions, though you're not translating it. If you want to translate it left and right, you gotta use the Shift key. All right, so looking at the staple, as we talked about before, there are atoms in it that we don't need. In fact, all we need are the beta carbons and then the intervening atoms. So all of the N-methyl and acetyl groups on either end we can totally get rid of, and we will. So I'll zoom in on one of those. I'm just going to use the red X to get rid of everything that's not the beta carbon. So I'm sort of paying attention. We're truncated down to the alpha carbon now. I'm deleting the alpha carbon. I'm leaving the beta carbon intact. If you ever want to get off the X key because you're afraid you're going to delete something, just press the question mark in the ruler. That's sort of a key that allows you to use Gaussian to ask questions about, oh, what's this bond length, without actually changing anything. So now we'll go to the other side of the staple and start deleting things. And again, it's everything that's not the beta carbon. So there we are. Okay. At this stage, I'm almost ready to make the new bonds. One of the problems, I want to try to be as realistic as I can. I'm going to be relying on the clean function of Gaussian to get things right, but there's a chance it could screw up the stereochemistry, and the only stereocenters we're going to have in this staple is the alpha carbons. And so I'm going to try to position, do you see how I've got an alpha carbon here and the proton is sort of up? I'm going to try to position the beta carbon on this lower side of that alpha carbon so that the system isn't tempted to change stereochemistry, and you can check it after the fact. The other thing is that you can see this beta carbon on the end here is, oh no, undelete. you can see the beta carbon on the end. Oh, I can't see it. There it is sort of the place where the new connection would be. It'd be over here on this side. It's sort of pointing in the wrong direction. So what I'm going to do is just rotate around this carbon-carbon bond to have the beta carbon pointed in the right direction. To change dihedral angles, rotate conformations, I identify the bond I want to rotate around, which is between these two atoms. I click one atom on the one side, I click the two atoms of the bond, and then I click one atom on the other side of the bond. That opens up a window that allows me to change that dihedral angle. And if I want to rotate around the bond without moving anything else, I'm going to fix group 1. That means group 1 and everything else is going to stay in place. And I'm going to choose rotate groups for atom 4, which will then allow me to drag this and rotate around that bond so at least the beta carbon's pointing in the right direction. You can do that. If you press cancel, it'll go right back to the way it was. If you don't press cancel, or you have to press OK, then it'll make the changes permanent. I'm going to do the same thing on the other side of the staple. Again, rotating around, this bond. And again, it opens up a dialog box. Fixed on atom 1, rotating on atom 4, just rotating around it a little bit. Okay, so now I'm almost in place, only somehow I unhighlighted the two amino acids. So I'm a little bit worried about myself, so I'm going to come back here. This time I'm only going to highlight the alpha carbons. So that's the alpha carbon of glutamate 7, and then the alpha carbon of lysine, whatever it was. 39, the alpha carbon of lysine 39. So there we are. So what I'm going to do now is create a new bond between the beta carbon here and the alpha carbon here.
So much to look at.
It is. I'm going to try to slide it over so it's a little bit less to look at.
I'm getting it, but
you getting it?
Like, yeah.
Okay, so I'll come up here to the menu bar, and I'll click the arrow between the two spheres. Click the beta carbon here and the alpha carbon there. That opens up this dialog box, and I'm going to click single bond. And there you can see it illustrates with a single bond. I'm going to click OK. I didn't even have to tell it what bond length I wanted.
Obviously.
It's going to take care of that later. And I'm going to do the same thing here with this alpha carbon and that beta carbon. Again, I just have to click on the one and then on the other. Click that. There's a bond there, and click OK. All right. So we've got the pieces in place. You'd be tempted to press the clean button first, but don't, because there's some things we know about protein structure that Gauss view doesn't know by default. The clean function of Gauss view is going to try to minimize the bond lengths. Is going to try to get physically reasonable bond lengths. So it's going to correct this and bring the staple into place. It will do a limited amount of moving of the molecule to relieve steric clashes. The other thing it's going to do is it's going to go through and change bond angles to meet what it expects for an idealized sp3 carbon versus an sp2 carbon versus an sp3 nitrogen. And unfortunately, if you look at the amide bonds in our structure, this is annoying, and I don't know what to do about this, but I haven't found a solution to it. If you look at the amide bonds in our structure, there are some of them, like this one. Oops, sorry. If you want to move the whole thing, you press shift first, then click, then you can drag. This amide bond's got partial double bond character. So when we press clean, Gauss view is going to say, hey, I know that the bond angle should be 120. I know that the dihedral angle should be planar. However, if you look at some of the other amide bonds, they don't. And so Gauss view is going to be tempted to do some non-amide things with those. So what I've learned you have to do at this stage before doing anything else is press save. And that's going to save all the changes that we made, put the new atoms in, go ahead and overwrite. But then we got to go through, and this is the painful part, and we got to edit all of the amide bonds to have partial double bond character. So let me show you how to do one, and then I'll delete the, then we'll stop recording the video because you don't need to watch all of that.
Time lapse.
Right. Do you watch Phineas and Ferb?
I did, like, years ago.
Well, yeah, it's old. So we need the quirky worky, zooty up, montage to do things quick song. Okay, so as with making any other or changing any other bond, you're going to click on the carbonyl carbon and the amide nitrogen. That will bring this up. Then you click this one, which is partial double bond character. We don't want to say that it's a double bond, but partial double bond character works. Now, the annoying thing is, you got to do this all in one sitting because if you save it as a PDB file, there's no information in PDB files about bond multiplicity, like double bonds versus not. So you can save this as a .gjf file, which is a Gaussian job file, but there may be some back and forth issues in going from that to PDB. I haven't encountered them before. So I try to do this all in one sitting. I've learned by sad experience that if I modify all the bonds and save and come back later, they're all gone, and that's because they didn't get saved. So I'll just go down the rest of the amide bonds and click them, and there's, you know, this is a 30 mer or 35 mer on either side, so you're going to do this about 70 times. And you're also going to do it with the indole side chains of tryptophan and the imidazole side chains of histidine. You see there how Gauss view doesn't really appreciate that histidine should be planar and aromatic. If you do clean, it's going to turn this nitrogen into an sp3 nitrogen with the hydrogen tilted out of plane. So all you do again is just click on the atoms. None of this changes anything to do with like bonds, charge. It just is a way of telling Gauss view what you want. Oops, that was what happened there. No, how did this happen? Did we press the, there we go. We must have pressed the red X again. It's just a way of telling it what you want the geometry to be.
Do you mean to do this on the staple?
No, because all of that's already done for the staple. Ultimately, I think a lot of this would get fixed anyway in Amber because Amber knows what amide bonds are, but I like to start out with something that's as reasonable as possible. All right, so go ahead and pause the recording while I montage ahead and do that. Amide bonds are, we've told it what we want for the amide geometries. What we're gonna do now is this isn't necessarily useful. I'm gonna save this as something else. I'm gonna call it pre-clean because I'm gonna press the clean button in a minute. None of what we've done outside of Gauss view is going to be saved, but it continues to persist in this open window. Then I just come up here to the broom button and I press the broom button and you'll watch things snap into position.
Ooh, that's cool.
Yeah. And it'll make some local adjustments. It's not changing a lot, but you can see it changing some of the atoms. And then it's done. And again, this is mostly a hypothesis. It's not anything real yet. And sometimes it comes up with some weird stuff. So, for example, if we zoom in here, you can see that it's generated a kind of strange steric clash with what looks like the C-terminal acetyl group. So that's easy enough to fix. All we need to do is come here, and I think we want to adjust this bond between the acetyl nitrogen and the alpha carbon. So I'm going to click the 4 atoms that are centered on that bond. I'm going to fix atom 1 and then move atom 4 around, and that should, it's not perfect, but that's going to at least get the acetyl group out of the way. Now, is
that a pretty common clash? Well, I guess not necessarily.
No,
because
I haven't.
Is the one on the
yeah, I haven't necessarily seen that before because that's on the N-terminus. But anyway, it'll figure that out. But that's good enough to begin with. Mm-hmm. So now I'm going to just save that as post clean. And now all the atoms are there, but we've got to get them in the right order. And to illustrate this, and you got to leave in like 5, is that right? To illustrate this, I'll just show you the atom list. If we zoom in and look at the lysine side chain, we're going to call this a propargyl glycine residue, but only the alpha carbon's there. If you see on the atom list. And the same would be true for the other one. And if you scroll down and look, there's a ton of atoms at the bottom that are the propargyl glycine residue and then the staple that are unlabeled. So we have to go change that. And we're going to do that in a text editor. So it's helpful when doing this to have the text editor open at the same time as you've got Gaussian open, at the same time as you've got the atom list open. So to do that, I just right-click on the post-clean file here and say open with a text editor. And that will bring this, I don't need that. And again, you've got atom number, atom name, residue number, and then coordinates. You don't need to worry about it. Anything that PyMol doesn't really recognize as being a natural amino acid. From a natural amino acid, it labels as het atom for heteroatom, though that distinction's kind of weird. Okay, so the first residue we changed was this glutamate 7. And what we want to do here is make space for the other atoms of this now propargyl glycine residue, and we want to rename this as propargyl glycine. So I'll just go through and do that. And as I told you, the 3-letter code for a propargyl glycine residue in an X4X staple, based on what I've done so far, is PRB, just because I needed something. Oh dear, where did the carbonyl carbon of that glutamate go? Huh. We lost the carbonyl carbon of the glutamate residue, glutamate 7. I don't. Also lost it for the loose. It is there, so that's weird. And we may need to find it. I'm actually going to close this without saving. We'll come back to the atom list and see. Something may have gone wrong in the something may have gone wrong in the clean things, the cleaning. So I will, that's why I saved the pre-clean so I can always go back. That was clue 7. So I see carbon, nitrogen, proton. Huh. So what I want to see is what's this one? 1, 2, 1, 4. Somehow it got confused about that, possibly because of a steric clash here. I don't know what's going on there or why that is. I'm gonna, since we've already saved this post clean, I'm gonna reopen it up and see whether we can see a problem in the pre-clean. Okay, now it's mad at us because it's got some problems with some of the way we've named residues. And it looks like the problem's already there. Oh, did we accidentally delete something and then it came back?
The only thing that I ever deleted was hydrogen.
Okay. Well, it doesn't matter. We can fix it. But you got to go, right?
Probably.
Okay. So we'll pause there and clean up the PDB file with a text editor so that all the new atoms are in the right locations with the right residue names and numbers and atom names. And sometimes we found that there's some weirdness that we've got to correct. So the residue that we altered is this glutamate, and we realized that the carbonyl carbon went somewhere, and we don't know where. So, but we verified that actually it's still there, it's just not showing up, and it probably has to do with Gauss-Fu getting confused by the fact that the carbonyl oxygen, where is that? Anyway, probably has to do with this weird steric clash there. So, and you'll notice that some of the connectivity's off. The bonds are no longer all in place, and that's partly probably because we've changed the name, and so Gauss-Fu doesn't know what to do with a glutamate that doesn't have all the regular side chains.
Is that a double bond right there, or does it have the...
This should be a carbon oxygen. That's interesting.
Yeah, because that's kind of odd.
Yeah, we'll fix it. It won't matter really in terms of.
Is that other one like that
Oops.
too? No, that one's normal. Okay.
Yeah. Okay. So what we'll do is come to the text file. You'll open up the PDB in the text file, and sometimes I like to just return a line so I can keep track where everything is, and I'll delete it later. But the first thing I'm going to do is just type in the new residue name, which for the stapled molecule, the propargyl glycine residue in the stapled molecule is PRB. The next thing I'm going to try to do is find the missing carbonyl carbon. I think we maybe verified last time that it's at the bottom. So what I'll do, I've got these two weird lone carbons, and that's not it, but that is. So that's atom 1214. So I'm going to scroll down here to the list, find atom 1214, and literally just cut it out of there and then paste it there. The order of atoms doesn't really matter, but I like to have it in H, C alpha, H alpha, then the side chain, and then C and O. So as before, I'm going to copy, or I'm going to type the residue name and number there.
Does it stay het atom?
Likely when Gauss view sees this weird residue name, it's going to turn all of those into het atom too, and that doesn't matter for amber, or really for pymol, as long as you've got the connectivity information. What's interesting with PDB files is in pymol, as long as you have a standard residue name, it knows what's connected to what, so you don't need to put in connectivity information. Okay, with that, then we've got the carbonyl carbon. Now we need to get the 3 side chain atoms, which are going to be here, the beta, gamma, delta carbons, and delta proton. All of that is going to count as the PRB side chain. So I need to find where they are, and the tricky part is that the staple sort of has 2 ends, and so I'm not sure which is which. I just start clicking. This is the beta carbon and the 2 beta protons. I see them there.
So can you just click in the actual file and click on the atom? In the Gauss view? Or Gaussian?
Could you click on the atom here and have it be highlighted here?
Or
I'm
just
not
see
sure.
what number it is.
Can you do that? I think so, with this little arrow with the clicking button. I think. Yes, you can click on something if it's not already selected and see what it's.
Just in case I was like getting lost, kind of.
Yep. So it looks like atoms let's see, 1168 through 1173 are the beta carbon and its protons, gamma carbon, delta carbon, and delta proton, which will get us into the triazole part of the staple. So I'm going to go down here and just select atoms 1168 through 1173. I'm just going to cut and then scroll back up to residue 7, which is my PRB residue. And in between the line for the alpha proton and the carbonyl carbon, I'm just going to paste. And then I'm going to start naming atoms. Now, how do you name the atoms? All of this is sort of, it's not random, but you have to do it consistent with some kind of convention. So I'm going to show you the SI from the paper where or the manuscript that's submitted, where I got the parameters for all of this, and I'll sort of show you what the conventions are. That's too small as to be invisible. So that's a PRB residue. They're labeled with Greek letters here, but of course pymol and amber just use the regular Roman alphabet. So I had to go look up what the names are for the various atoms. So it'll be, let's see, Ca, Ha, Cb, Hb2, Hb3, Cg, Cd, and Hd1 for beta, gamma, and delta carbons. So I just come over here and I type, and this is where it's good to open up the atom list again in pymol and just confirm, I'm sorry, Gauss view, just confirm, okay, atom 1168 is the beta carbon, atom 1169 is the beta 2 proton, 1170 is the beta 3 proton, then C gamma, C delta, and H delta 1. With PDB files, you want to make sure everything's aligned with everything else. Like, that's how it knows what columns are. Yeah. So I don't totally know the number of spaces. You just keep it consistent. You've got some wiggle room in the atom names if you need more space, but the residue names all have to be here. And then I'm just going to make sure that the residue name and number is correct there.
So, I mean, I assume this is the same every time you do it, because it's the same staple.
Yeah. Yep, so every time you do this, it's going to follow this pattern. If you change the staple, it would be different. There, now that that residue is done, I can delete the spaces. Now I need to go find the next position where we made changes, which, yep, 39 is the first lysine residue, and you can tell because it's got the backbone atoms and nothing else. Conveniently, that one has the carbonyl carbon. We're going to have an extra carbonyl carbon that we got to get in the right place because I saw it.
The one next to.
It was like the leucine, wasn't it?
Yeah.
Yeah.
Next to the other one.
All right. For now, we'll just center on these atoms. Oh, still got the other ones highlighted somewhere. Okay. That's good, so I'll go down to lysine 39. And again, just going to edit the...
It's kind of convenient that these ones are at the beginning.
Yep.
Because...
Yeah, they're easy to find. Okay, and we're going to get the side chain there. I'm going to scroll down to the bottom of the atom list editor. I'm going to notice
but that's because
these are the missing carbonyl carbons, which we took care of. We're going to find that these atoms 1207 through 1212 are the remaining side chain atoms. So I will go down the list here to 1207 to 1212 and just cut that out and scroll back up, paste it in place, and same thing. And this is, I was careful when I built the file for built the model for and derived the parameters for the staple, that I put all the atoms in a sensible order so that it would be easy to staple it in later. But again, we have beta carbon, beta 2, beta 3, C gamma, C delta, H delta 1. And it looks like that's that there. All right. The remaining portion of the molecule is just going to be the staple, except for this atom 1213, which we got to figure out what that is and where it goes. Oh, where are you? That was helpful.
That was not centered.
And our hypothesis is that goes to, I think, leucine 6, because leucine 6 looked like it was missing a carbonyl carbon. I see nitrogen, alpha carbon, and I see an oxygen. And indeed, that's right. 1212 is the carbonyl carbon, or 1213. So, whoops, I lost it, but that's okay. I didn't need it there anyway. So I'll take 1213, cut, and go up to leucine 6. I'm going to paste it right here by the oxygen, and I'm just going to make sure it's got the residue name. Okay, lastly, we're not, I mean, there's still some steps, but we need to deal with the staple. So the staple's totally unnatural. There's no need to name the atoms anything that makes sense, because according to any convention. But what I chose was to start on one side of the staple and just start numbering with Greek letters, starting with alpha at this ending triazole nitrogen. Now, the problem, that's a totally sensible thing to do, but the problem with that in if you want to look at your structures in pymol is if you have an atom that's named Na, pymol thinks it's sodium.
Oh, yeah.
So and amber isn't going to get confused by that at all, I don't think. But we want to generate figures in pymol, and it's annoying to have to go in all the time and tell it. So what I decided is just to give it a different name. So I chose a letter that wasn't going to be used for any other purpose, and also is not the symbol for a chemical element. And there's a few other times we have to do that, but this is one of them. So the first nitrogen is NF. And again, because all of these definitions go into the Amber library file so that Amber knows what charge goes on each atom, you do have to use these names.
Okay, wait, sorry, I'm just trying to understand this graph. Type NC,
okay.
Where is that?
I haven't talked about that yet, so we're just talking about the atom names. This is a charge, and this is an Amber atom type.
Okay, that doesn't, like, that's not
That's for later, no.
Okay.
Yeah, and I'll explain that. It's not later. It's not too bad, but
so this atom
is the alpha.
Okay.
Alpha, beta, gamma, delta. It makes sense except for that one. And again, it's if I called it Na, pymol later on was going to get confused.
Okay, I just wanted to explain.
So a couple of other features of this staple has some symmetry, right? This nitrogen is the same as that nitrogen. And I've constrained the charges to be identical. So you might ask, does it matter which end of the triazole I call NF and which end I call N, whatever it is, R? No, it doesn't. Because if you look at the charges, they're exactly the same. Okay. So I'm going to just go through and I'm going to edit the names of the staple atoms, NF and B and G for gamma, C delta, that's that one. And because they're all in order, if they weren't in order, I would have to go through and click on an atom in the Gauss view, but because they're all in order, I can basically do it on autopilot. C, E, and proton E2, and E3.
To know if they were out of order, it would just be like you would have a carbon after the hydrogen. Like, how would you know if the hydrogens are out of order? I guess they're the same, so it doesn't matter.
Well, you wouldn't know that anything was messed up unless you came down here and you. Oh. There it is, and then you start clicking on stuff. Oh, what's with this strange atom geometry? And see that, oh, it's doing the exclusive highlighting. Whoops. Clicking on stuff and just see that it's in order.
Okay. Do you check that every time?
No. Because I know that they're in order in the file that I pasted them in. So you can probably just count on them being the right order. So I just got to keep plugging away with the atom names. OZ, that's, I think, you can look up the Roman equivalents of the Greek letters. It's kind of dumb, but the reason I try to stick with that is because they use that for all of the amino acid side chains. Like, you've ever heard of somebody talk about the lysine epsilon amino group? That's why. Now, this one, CV, that's a weird choice. We're at the lambda carbon. And that's another situation where if I put Cl, pymol later on is going to think it's a chlorine. And that's not going to change the amber calculations. Amber's smarter than that, but Pymol is not. And just to make it easier later on to make figures, it's convenient to choose something different.
So you said the placement of this one doesn't really matter.
Of where in the PDB file it is? No. I'm counting it as a separate residue, and it's totally at the other. It's just after the molecule. If you want in Pymol, or you can, or in a PDB file, you can specify what chain something goes to. So before I have in other times, there's a chain designator that goes here, and I called the first subunit A, the second subunit B, and then the staple chain C. Amber doesn't need or use chain designations at all, so I stopped doing that. It can be convenient for manipulating Pymol files, but it's not that necessary. So we're going to call this residue PZ4, and we'll call this residue number 75, and then I just have to paste that in below a ton of times. That will make sure what we're doing now is ensuring that Amber later on is going to know we've got a coordinate for every single atom, and we know what every single atom's residue name and atom name is, so that Amber knows which charges and parameters to use. One of the things we messed up here is the order of atom numbers. And that's kind of a problem because, at least for the unnatural residues where connectivity isn't obvious, there's a list at the end of the PDB file that says what's connected to what. And we've kind of messed with that.
When did we do that?
Well, we didn't mess. We just messed with the atom order when I cut and pasted stuff that was down on the end of the list up to earlier.
The case no matter what then?
Well, no, we're going to fix that, but Gauss-U is going to do it for us. What I'm talking about is if we go to look at...
But like every time you alter this PDB file, that's going to happen.
If you copy and paste and move, that is going to happen, yeah. So at this stage, I'm just going to press save. I usually save it as something else. So... NR is the last nitrogen. Okay, well, I sort of screwed up, but that's fine. All right, I normally save that text file as post clean with a dot and then edited, so that I know at what stage I'm at in the process. I edited the PDB file. Now I'm going to close the window in Gaussian, and I'm going to reopen the edited PDB file in Gauss-View. And I'm going to reopen the atom list. And one of the great things about Gauss-View is it's automatically going to renumber the atoms for us and get them in the right order. So I will at this stage save the PDB file from Gaussian, and I'm going to call this edited.resaved, and that lets me know the numbers are going to be right. I can go back in and open that up with a text file with the text editor, and if I go down to that leucine residue, you can see, or sorry, the PRB residue, you can see that where I had numbers in the thousands that are now renumbered. The other great thing about Gauss-View is in the process of renumbering, it's going to get all of these connectivity numbers right. These are all of the connectivity information for the unnatural amino acids, the unnatural atoms. If we now go back to the...
Really quick, how did you open the PDB file, or how did you save it in Gaussian?
Yeah, you just go up to the save bar and press save, and then you can there's a place where you can change what kind of file you're saving it as. If you wanted to save it as a Gaussian input file, you would choose that. I choose PDB. Yeah.
Okay, sorry, thank you.
Nope, that's fine. Let's see. If we look in Gauss view at the end of the molecule where the staple is, we can look at sometimes as we've changed residue locations and designations, sometimes we're going to get some problems on the connectivity. So, or it's going to leave out some bonds that are supposed to be bonded to each other. This can be difficult to see, so you sort of have to look at it. But one of the things I notice is, why is it so hard to see? The unnatural PRB is kind of messed up. The atoms are all there, but it doesn't know what's bonded to what. Now, I think that Amber's going to be just fine with this. It's not going to be a problem, but it bothered me, and so I'm going to show you how to fix it. Here are all the atoms in the PRB residue. You can see we've got bonds for all of them, only the alpha carbon 98 is not bonded to the alpha proton or to the nitrogen 96, and then nitrogen 96 is not bonded to its proton. So all we do to change that is we open up the now resaved PDB file that has all of the right atom numbers. And we come down the list of connect and we see atom 98, which is the alpha carbon. And we see that it says that it's bonded to 106, which is the carbonyl carbon, and to 100, which is the beta carbon. It needs to be bonded to 4 things because it's an sp3 hybridized carbon. So I'm simply going to add 98 or 99 there, which is the alpha proton. And I'm also going to add 96, which is the amide proton, or amide nitrogen. And I got to get the spacing right, and you just sort of follow what's necessary to make sure all the numbers are lined up.
Okay, that's 96. Sorry, it's hard for me to see. It looks like a 95.
Yep.
Okay.
The other thing we're going to change is amide nitrogen 96 says it's bonded to previous carbon, presumably 94. We need to say that it's bonded to proton 97 as well, and then also to alpha carbon 98. And it's okay for that. So the way the connectivity term is, this is the first atom is the one you're talking about. Everything else is what it's bonded to.
Yeah. Does it matter what order you
Nope.
put those in?
Nope. So I'm going to press save on that. Then I'm going to look. The places it usually gets wrong are places with unnatural residues. I previously noticed earlier that the leucine seemed to be messed up. I don't think it is now, but I'm just going to highlight the leucine to confirm that it's all fine. Shoot, there are a ton of atoms in leucine. Oops. And that looks mostly fine. Which hydrogen?
Right by 96. Oh, that's the one that we just did.
Yeah.
Right?
Oh, yes. That's right. I shouldn't have clicked 96.
Yeah,
it's still down there. All right. Yep. Okay, so that leucine looks fine. And now I'm going to do the next propargyl glycine staple residue just to see. It probably will make a mistake in there.
I think it did. At least I saw one.
There we go. So center. All right. Yes, it looks like it's got problems on the amide nitrogen and alpha carbon. So we'll just come over here to the text editor. We'll find atom 566, which is the amide nitrogen. It says that the amide nitrogen is currently bonded to 564, which is probably this carbonyl carbon. That's fine. We need to add 567, which is the alpha proton. Sorry,
Sixes look so much like fives.
Yeah. And then we need to add 568, which is the alpha carbon. Then for atom 568, it only shows it being bonded to beta carbon 570. So we need to add to that 566, which is the amide nitrogen, 569, which is the alpha proton, and 576, which is the carbonyl carbon. With that, we can press save, and then if we reopen that in Gauss View, we can check and see whether we messed it up or whether it's fine. And you can see now the bonds are all in place. There we go. So you can see that in our propargyl glycine residue, we've got everything bonded correctly. And then we can check the other side and see if that's similarly the case, and it looks like that's not the one, but that is. Yeah, it looks like everything's good there. All right, the last thing I'm noticing that makes me worried just a little bit is that, oh, it looks like the triazoles were sort of not, it looks like we should have gone through and edited those, because it's, if you see what it did there, it's making that a little bit longer because it thinks that's a single bond as opposed to something else. Amber's going to fix that in the minimization process. I don't like that steric clash there.
It also is not the right character. It's like not a...
Right.
That amide.
And that's just Gauss View interpolating what it should be, because there's no... Yeah.
Just barely. But...
what I'm going to do here is dumb, but I'm kind of worried. Oh shoot, what did I just add? I added a carbon. How did it do that? I want to change the conformation a little bit, but I'm not totally sure how to do it. And so what I'm going to do is highlight those bonds and change the dihedrals, and I'm going to change these to rotate groups. I don't want to do that because that basically moves the protein around, which I don't want to do. Maybe I'm just going to trust that it will fix that. Okay. So that's the process. Now that we're at this stage, we don't need to save anything because it's fine. And we're ready to do the prep for amber, the PDV for amber thing. So we'll go ahead and pause there. Oh shoot, were we not recording anymore? I thought we were. Oh no, there it is.
It looks like it.